So I'll try to run through these slides relatively quickly. I know not everybody is all that keen on slides. I tried to take out most of the marketing gunk and just focus on the technical stuff. One way to think of Ocarina, the elevator pitch, is we're a disk space factory. So we chug through a bunch of stuff and we create free space. So if we're going to talk about compression, we're going to talk about dedupe, we're going to talk about ways to create free space on disks that you already have. We don't sell storage, we make free space on storage that you already have. So you can think of us as sort of like a factory with smokestacks, chugging away, creating free space on storage that you already have from the vendors that you already buy from. So just a little background, we've been around for about 3 years now. We've won a good handful of awards. I'm not going to go into all this stuff. We're going to talk a fair amount about our partnerships with storage companies, because one of the things that I found in 20-something years in the storage business is that storage is quite a bit different than servers in the conservatism of the storage buyer and the storage admin. Whereas people will swap out servers, from 1 week to the next based on who's got the best price, and it's all pretty much commodity, whether it's a Dell server, an HP ProLiant, or whatever. Storage tends to be a lot stickier. People like to stick with their vendors. How you manage it, how you provision it, how you do all these things is different from vendor to vendor. They build up relationships, and people are much less likely to just from 1 week to the next say, well, I'm throwing out EMC and I'm going with NetApp, or vice versa. So consequently, one of the key things of our strategy was to build a technology that integrates with the storage that you already have, with the vendor that you already have. That we're not trying to talk you out of switching. And so towards that end, we wanted to bring our technology to the people who make file serving solutions. And these are the ones that we've announced so far: HP, BlueArc, Hitachi, EMC, and Isilon. There are a couple more coming, and by having those partnerships, we're able to more deeply integrate our stuff into their storage. And I'll talk about how that works. And then, just so that you know that we're not lying about everything, I put some names of publicly announced customers. They're all referenceable. And mostly big names. We started, our first deployments were all in giant data centers, sort of petabyte-sized data centers. Unlike a lot of startups who start small and then try to work their way up the food chain, we started with the biggest data centers we could find, and we're sort of working down the other way. Skip that. So what is it that we actually do? The thing that I'm going to describe here is called the ecosystem. That's the name of our solution of how we create free space. It stands for extract, correlate, and optimize, and I'm going to describe those 3 steps in a fair amount of detail. But at the end of the day, what we're doing is a combination of compression, and specifically content-aware compression, where we recognize the specific file type and apply compressors that are unique for that file type. We do deduplication, and again, this is a little bit a content-aware deduplication, where it's different than the kind of dedupe done in backup, like data domain and that sort of thing. And I'll explain a little bit about the differences. And then the third thing is we've tried to build this in a way that you could deploy it and have its deployment be invisible or transparent to users and applications. So the fact that somebody went through and shrank all their files is not going to be evident to anybody. Now, as a little background, I borrowed these next couple of slides from IDC, an analyst firm. We've done some work with them, and one of their analysts, Noemi Greitsdorf, did a presentation on the different forms of data reduction out there. And so I thought I'd share those as a little bit of a background before we talk about what we do specifically. Compression is something that you can do to a single file. So, with compressors, you can give me one file, and I can run a compressor on it, and I'll give you a smaller file. There's some interesting things that are worth knowing about compression. One is that it's all about prediction. So a compressor will go through a file looking for patterns and trying to predict the next value in the sequence. If you can predict that next value, you can compress the file. And so you can have generic compressors that you can try to use on any kind of file, or you can have content-aware compressors that sort of know in advance, oh, for this kind of file, these are the kind of patterns I might expect to look for. And you don't need 10 files to be able to do compression. You can do compression with even a single file, and of course compressors have been around almost as long as computer science itself. We'll talk a little bit about what we're doing different in compression. One thing that we think is interesting is that compression doesn't preclude doing deduplication, so you can do compression and deduplication, but they do sort of pull against each other in an interesting way. And that way is this: if you want to find the most amount of duplicates, you want to look for the smallest chunks, right? So the smaller the chunk is you're looking for, the more likely you'll find duplicates across files. In compression, you want to look at the biggest possible chunk because there's more likelihood that you'll build up good context and make good guesses about what's next. So when you're talking about doing dedupe and compression, there's a little bit of a trade-off about what size you look at, and I'll talk about that in a second. Single instancing is the most primitive form of deduplication. This has been, for example, around in Windows storage server for quite a while. This means I'll go through a volume or a set of volumes, a bunch of files, and find exactly identical whole files. So instead of looking for duplicates inside a file or for subfiles, I'm just going to go see if there's two exactly identical files. They might have different names, but otherwise the whole file is the same thing. This is actually pretty easy to do, and lots of people do it. So that's called whole file single instancing. It's worth saying that if you're doing subfile dedupe, you automatically get whole file single instancing because all the parts of a file will be duplicates, so you dedupe them all as a side effect. Then you have the kind of dedupe that everybody's been talking about for these last couple of years. It became really hot with backup first, and that is you have a whole bunch of different files. So in this case, there's 1, 2, 3, 4 distinctly different files, but within them, there are sections that are the same across different files. And so in this case, I've represented, or Noemi's represented, each file as a series of chunks. Chunks can be different sizes, but here's a chunk called A. That chunk of zeros and ones also appears in this file and this file, and so those are duplicates. Now the question about dedupe is, can you find those? If you can find them, then instead of saving that chunk called A 4 times, you can save it once and have each file point to that one copy of A. And for the most part, that's a lot more space efficient than saving A 4 times.
Question.
Yeah.
Would an example of that be, say, a Word document with the same overlay graphic for a company logo on a bunch of different
Absolutely. Okay. And there's lots of nuances with this dedupe, and we'll talk a little bit about those nuances when we talk about how Ocarina does this. But you know, if you dedupe that stream, you would end up having stored each of those chunks only once, and then the files would be you know, pointers to those chunks. Now, one of the things might be, oh yeah.
You say chunks. How do you define chunks? I'm guessing it's not the same as a block.
So this is a big difference between one dedupe implementation and another. Now here I'm just talking about generically, but it does vary from vendor to vendor. So for example, with NetApp, they have NetApp dedupe built into their filers that looks at 4K chunks that are at fixed boundaries in their file system. So it's always 4K, and it's always aligned on file system boundaries. Now other people will have what's called the sliding window. Well, they'll take a window of some size, and it's like, I don't know, you're probably too young to remember this, but there used to be these things called slide rules that would have like a little, you know, plastic thing that you slid across. Well, in sliding window dedupe, you would take a window and slide it across the zeros and ones. And so wherever those let's say that that window was 4K. If you slid that along, anytime you found a match with another 4K, you would dedupe it. So in the first case, that's fixed window, fixed size chunk. This next case would be sliding window, but fixed chunk. And then you could have sliding window and also sliding size of the window as it moves along, right? And that's the most complicated. And in a sense, that's what we do. And we also do a further thing called object dedupe, which I'll describe when I talk about how Ocarina works specifically. But in any case, that's the idea. So you find things, you find matches. Now, if you have the fixed size, fixed window dedupe, a good example would be, let's say that this is a Word document, and that's a paragraph, right? And so that paragraph is exactly the same as this paragraph in a different document, right? Now let's say that I add one word to the start of that document. In a fixed window or a fixed block dedupe, if I added a word at the start of this document, it's going to shift everything over by whatever, 7 characters. All these blocks will be slightly different. You would miss the dupe, right? If you have a sliding window, then as you slid the window across, even though that it moved a little bit, you'd still find that duplicate. So it's a big difference. The fixed block solutions are dependent on data not changing very often to be effective.
Cheaper to run, aren't they?
What's that?
Mathematically cheaper to count.
That's true. They are easier to calculate the hashes. So it's worth pointing out. So how do people find these matches? I don't think I talked about it anywhere else. How you find the matches as you calculate a hash value for each thing that you're looking at. And then you look it up in a table to see if there's something else you've seen before that has that same hash value. And so it is the easiest to calculate a fixed block. And you know the hash value for every block. When you slide the window, you have to recalculate a hash. Every time you move it, you have to calculate a new hash. So there is more
So you
calculation
accelerating that in
overhead
silicon,
for
or
that.
are you just doing it in software?
What's that?
Are you accelerating that math in silicon, or are you just doing it in software?
At Ocarina, it's all software.
Right.
Do you do that with movies as well?
We do. So I'll talk a little bit about rich media in general here in a second. So Ocarina's our specific form of doing data reduction we call the ecosystem for extract, correlate, and optimize. And of course, we stood on our heads to get the acronym to come out to be, eco, ecological, eco, whatever. In practice, you could think of this as extract, dedupe, and compress. But that doesn't make a good acronym. So let me describe how this works and why it's a little bit different than what anybody else is doing. And it really, probably the most important difference comes from this very first step, which is extract. Everybody else is doing whatever it is they do, compression, fixed window dedupe, sliding window dedupe. They're doing it on the zeros and ones that are on disk. So you've got a disk in your storage. On that disk is a bunch of zeros and ones that represent the files, and they're looking through those zeros and ones to find duplicates. Well, the thing is, in backup, that's very effective because backup is repetitive. You back up every day, so consequently, there's going to be tons of duplicates on disk from Monday to Tuesday to Wednesday to Thursday's backup. Easy to find, low-hanging fruit. If you're talking about online storage, where you probably only have one copy of every file, you're not creating a bunch more copies every single day, the dupes are harder to find. And one of the reasons they're harder to find is that most of the file types that drive storage growth today are already compressed. So for example, in Office 2007, Microsoft now compresses every document type, whether it's Word or Excel or PowerPoint, when you save. In Office 2003, that wasn't the case. In 2007, they compress on save. You often see the little saving, and there's a little bar that runs across the screen. That's them compressing the file. Video is always compressed. photos are compressed with JPEG. PDFs are compressed with a compressor called deflate. It can go on and on. As it turns out, most of the files that people store on file servers are already compressed in some way. Well, what do compressors do? They look for patterns. If they can find patterns in the file, they'll replace them. So if a data set has already been compressed, a lot of the duplicates might have been obscured by the compression. And so an easy example, if I could use the whiteboard for a second, and I'll take you through this on the thing. Let's say I have a graphic, some sort of, like you said, OLED graphic. Could be a GIF, could be a TIFF, could be a JPEG, could be, whatever, some little graphic. I store that on disk. Then I paste that graphic on page 12 of my Word document. And then I paste it on page 27 of my PDF. Same graphic, same size, came from the same place. All I did was copy and paste it. On disk, the zeros and ones for those 3 copies of that graphic are going to be totally different. Not findable by standard dedupe at all. Why? Because this was the original. This was compressed with some version of zip that's inside Microsoft Office. This was compressed with deflate. And so because those have all been compressed with different compressors and stored in those different file formats, now I've got 3 copies of that graphic, but there's no dupes in the zeros and ones on disk. So what do? We extract. We start with a file, and in this example, I'm starting with the zip file, which is the worst case. It's compressed, and it includes a bunch of different stuff. So I'll decompress it. Inside that zip, I found 3 different files. Guess what? They're all compressed too. So I'll decompress those. And then inside there, we'll find what we call objects. Here's some text. Here's a graphic. Here's a photo. And we will keep going in this extraction phase recursively over and over and over again, decompressing things, breaking them apart, finding the new things, and if those are compressed, we'll decompress those. We'll keep going until we get to the raw information inside each file. Now, as the output of that, we have a string of zeros and ones. This is a different set of zeros and ones than the ones that are sitting on disk, right? These have been decompressed potentially multiple times. Now, we start looking for dupes. So now,
I have a quick
question. Yeah.
Is this? I kind of missed the first couple of slides, but is this an appliance-based solution? And if it is, do you put it as a gateway somewhere, and all the data goes?
It can be an appliance or it can be software, depending on what storage you have. So the default case is it is an appliance, and I'll talk about the deployment choices in a second, but basically we read files off of your existing storage, we do all the stuff I'm talking about, and then we write the stuff back out to the same storage.
Oh, so you take the data, you
shrink it, and then we put it back. Yeah. So we don't store anything in our appliance. And in fact, when I talk about this extraction phase, one of the things you're immediately thinking is, oh my God, he's making that stuff 10 times bigger, right? So you're going to use up more disk space. Well, we don't actually store any of this. This is all happening in memory in our process or on our appliance. We're not storing this out on disk anywhere. So we do this decompression. Now, when we do that dedupe, we're sliding our window through a string of zeros and ones that are not the zeros and ones on disk, but they're the zeros and ones that come out of this extraction process. And so what does that mean? Well, that means if there's a JPEG, so in this example, there's a photo that's the same photo in 3 different files. On disk, the zeros and ones that represent that photo would have been totally different. But coming out of our extraction process, we're able to find that photo in all 3 different files. So we'll get rid of 2 of them. Now the other thing that we do here in this stage is we look for things that are similar. And why do we do that? We do that because when you go into the next stage, which is compression, if you group things together that are similar, you'll get better results in the compressor. So the next thing after dedupe, we route the chunks or the objects that we found through a neural network that determines what compressor is the best compressor for this chunk. And so in this example, I had text, I had pictures, I had graphics. Well, it turns out that we have compressors, different compressors that are better for each of those things. I think right now today we have 120 something compressors. And so, and those range from very generic, like a text compressor, there's 10 million of those. You can find them for free, open source, et cetera, to compressors that are as specific as, here's a compressor for a genomics, gene sequence file that comes off an Illumina gene sequencer, or here's a compressor for certain kinds of post-production files that get created in movie animation. So the neural network will figure out what a chunk is, route that chunk to the best fit compressor that we have for it, and then at the end of the day, it all gets stored to disk, and it's smaller. So first we extract, then we dedupe, then we route, and then we compress. And as it happens, you can turn off dedupe if you want to. For example, some of our customers are photo sites. Photo sites know they don't have any duplicates. All the benefit's going to come from compression. So they'll turn off dedupe because there's no reason to go through all that calculation. On the other hand, some of our customers have thousands of virtual machines. Virtual machines are great for dedupe because every virtual machine might have a whole copy of Microsoft Windows in it. It's all duplicate, so you might turn off compression to make it go faster and just use dedupe. So you can tune it, but the 3 steps represent what we do. Included in our algorithms are a whole bunch of special algorithms for images and videos. Some of these are bit-for-bit lossless, and that's the default whenever you turn on Ocarina. We do also give you the ability, as these photos posted on the walls represent, to do what we call visually lossless, which is lossy compression, but with the loss constrained in ways that the human eye mostly can't detect it. So that's why we're having the contest. Most of these photos here have been compressed by 50 to 70%. And I think you'll be hard pressed to tell the difference which one is 70% smaller than the other one. And usually people will say, oh yeah, sure, on a screen you can't tell the difference, but if you blow it up into a good quality print, it'll be obvious. So that's why we blew them up into good quality prints. And you can take a look and see. I'm not going to go through all the details. Suffice it to say that we have a bunch of very sexy algorithms for analyzing the chrominance and luminance of images, for reorganizing images according to like chrominance and luminance, and then compressing them. And afterwards, if anybody wants to talk about that in detail, we can do that. Otherwise, I'm going to run out of time if I describe all this stuff. Dedupe also applies to images in a way that has nothing to do with the way that dedupe works on a backup, for example, data domain. They're looking for matching blocks across files. Well, what about images? Let's say that I start with a photo, and this is a very typical photo that I would take because it has red eye. And every photo that I take always has red eye. I don't know if it's because I have a cheap camera or because I'm a crappy photographer. But let's say that I then open up that photo in Photoshop, edit a few pixels, and get rid of the red eye. What you'll find is, having changed only those few pixels, and I don't know if you can see it from where you're sitting, but now there's not red eye on her face, the zeros and ones for that photo are now completely different. Every 0 and 1, completely different, just by changing a few pixels, because the photo gets recompressed as it's saved. But if you have the original and the fixed up one, they're completely different patterns of zeros and ones on disk, but they're almost entirely duplicate visual information. what our algorithms can do is find the fact that these are almost entirely duplicate photos except for those pixels in the red eye, and dedupe at that level, at that image level. And so we'll get huge savings when we find similar but different images. And this applies to video, it applies to large collections of medical images, of satellite images, of consumer photos, etc.
Have you developed your own maths for that, or are you reusing someone else's libraries?
Yeah, these are, all of our image algorithms are our own IP. Our chief scientist, Matt Mahoney, is a guy who was a professor of mathematics in the academic world. His passion is entirely compression algorithms, and especially image compression. Yeah. And we were able to hire him away by saying, what if you didn't have to deal with pesky students and class schedules and grading papers, and all you had to do all day long was write image compressors? And he said, okay, sign me up. Yeah. And so there's lots of many patents we have in this area of image analysis and compression.
This would be the third or fourth rehash of this technology I've seen in the last 15 years.
That's right.
There's nothing new.
Yeah, it's
not new in the sense that.
That's right. It's the latest version.
Yeah, this is the latest version. You're doing it on the file.
Yeah.
But,
exactly.
And it sounds like it's more about the application, right? It's about applying the technology or the science behind it to really solve a challenge, not necessarily that, yeah, everybody's done it before.
Yeah, that's true. So, you know, for example, Mant's image algorithms are amongst these 100 or so algorithms that we have. And part of what our solution does is figure out which compressor to route a thing to. So, you know, in the case of the image ones, part of it is having Mant's algorithms, part of it is knowing, this chunk or object or file should go to Mant's algorithm and not to the seismic compressor or the video compressor, et cetera.
The content detection these days is pretty well.
That's right.
You know, a lot of those issues are solved these days as we're converging around a limited number of file formats.
That's right. And although one of the things that we found is that people lie, or not people, but systems. So you actually have to look inside the file to get it right. If you go by extensions or whatever, you'll often find something is called, you know, .doc, and really it's something completely unrelated. Just a few quick comparisons. The other big dedupe solution for online storage, and remember, we're for online, we're not for backup, is NetApp dedupe that comes as part of NetApp's system. So we took different kinds of data sets, home shares, a mix of kind of stuff you'd see on like a social networking site, media mix, life sciences mix, so pharmaceutical, genomics, mass spectrometry, that sort of thing, seismic data from oil and gas, and then a sequence of backup files from a week of backups. And we had a independent analyst come in and run our stuff in NetApp on the same data sets and sort of compare results. And because our stuff includes both dedupe and compression, we wanted to compare the following things. So the first bar here is the size of the original data set. The second bar is NetApp dedupe, so how much did NetApp shrink it? The third bar is Ocarina dedupe only. So turn off all the compressors, right, and just do dedupe. How do we do? So we wanted to be able to compare our dedupe with their dedupe head to head without throwing, give me the hook in the back. And then the last thing is if you turn the compressors on as well, what kind of results do you get? And they vary by, by what the mix of files are, and that's one of the reasons we're doing this exercise with the USB sticks, is to see the different kinds of results you get with different kinds of files. I'll skip this one.
So do you guys have a guy in a box that's sitting over in a laptop compressing files? Is that the solution you guys deliver to customers?
Yeah, that's the guy right there over there. Here's how it actually deploys, which is here's the box, and then Mike over there is the guy sitting inside the box. I will say this, that most companies our size talk about R&D, but what they really mean is R. So in other words, I mean with D, so they have developers. at Ocarina, we have a mix of R&D. So we do have several PhD mathematicians who are writing compression algorithms that have nothing to do with C code or that sort of thing. They're actually writing new fundamental mathematics. Matt Mahoney would be a good example of that. We have about 6 others. And then they give their stuff to people who actually turn it into running code. And where that code runs by default is on something we call the Ocarina Optimizer. That's an appliance. I don't know if we're letting anybody go in the machine room, but it's a 2U rack mountable thing with a green bezel on it. It sits on the network. It looks just like an AS client. It reads files off your storage into the appliance, does all that stuff I talked about to shrink the file. Then, and this is an important thing to wonder about if you're thinking about this space is, how do I know you're not screwing up my data? Okay, so you said it's 70% smaller, but how do I know I can get it back? Well, as part of our process, the original file, as indicated by the fact that the disk is still full, that original file is still sitting there on disk. We haven't touched the original file. In the appliance, we read the file, we did what we do to shrink it, then we reverse that and we expand it back, and then we do a checksum to compare what we expanded back from this to the original file that's still sitting here. If those things match, then we'll say, okay, we did a good job, and now you can replace the file that's on disk with the shrunken file. And so that 256-bit checksum compare is absolutely central to the sort of safety of what we're doing. Otherwise, if you didn't have those sort of checks in there, you could run through and shrink something by 70% and end up scrambling it in a way that you couldn't get it back. Now, after I've shrunk it, obviously users and applications need to be able to get it back. And so how does that happen? Well, that happens with something we call the reader. The reader is our rehydrator, decompressor, whatever we did to a file. The reader is how we undo it from the file. And it's faster because it doesn't have to figure things out. It already knows what was done. And the reader can live in different places. And this is really where we get into the storage integration. The reader could live on the same appliance, in which case users would come through the appliance to get their data back. For those storage vendors that we have a partnership with, we've actually implemented the reader inside the storage in some way. And so instead of having to come through our appliance, the storage itself knows how to decompress or rehydrate files that we've shrunk. And in that case, the optimizer is just a shrinker. No users ever go through it. The optimizer reads files, shrinks them, puts them back in storage. But when the user or an application wants to get their data, it'll be rehydrated for them by the reader that's embedded in the storage. And for the most part, we've found that customers like that if there's an embedded version for their storage. I'm not going to go through this detailed data layout thing because Mike is waving the time button at me, but Gu, our CTO, can talk about it if you're interested. This is how and where we store the compressed and dedupe files on disk. And I'll send these slides out if you want. We do have the option of reading from one storage platform, shrinking the files, and writing them somewhere else. We call that optimize and tier. And one of the reasons why this is worth talking about, and we're our co-partner for today's event here is Nirvonics. One of the things you can use us for is to read files from a primary storage platform that's in your data center, shrink them, and write them out to the cloud. And by having shrunk them, you're doing two things. There's the obvious thing of saving disk space, but now if you've shrunk it at the customer site, when you go and it passes the checksum and all that stuff, now that thing is going to get written to a target volume that could be in the cloud. The size of the data that you're having to write over the WAN is now drastically smaller. could be 70, 80% smaller. So you not only get storage savings, you get bandwidth savings. And that makes, in a lot of ways, can make using the cloud as a nearline or archive storage target a lot more feasible because of the network bandwidth reduction that you get.
Wouldn't that rely on the fact that the cloud provider that you're putting it to isn't using any bandwidth optimizing technology to accept the data from it?
So if you put like a riverbed or something in between, that's transparent to us. So in fact, we do test with riverbed here routinely. We don't test with all of them, but riverbed is sort of the most commonly used one. And so if you put riverbed on the wire in between us and them, it works fine. It does work best if you have a partnership with the cloud vendor, so that, for example, let's say that I did this and now this data center burned to the ground. And now I've got a bunch of compressed data sitting at Nirvanix or whatever. How do I get it back? Well, it would be good if the cloud vendor had the capability of reading back compressed files in the cloud, and so that is the case with Nirvanix. And I guess, well, that's the only way, that's the cloud vendor we have a partnership with.
Real quick question, on the eco reader, like let's say a file is on disk, you realize decompression efficiencies on it. I want to pick it up and look out and send it as an email to somebody.
Mm-hmm.
Does it reflate?
Yeah.
Because they won't be able to realize.
That's right. So there, this is actually a very good question, because in the normal case, every time a user or an application wants to read a file, we rehydrate it. So we give you back bit for bit exactly the file the way it was in the first place. And so if you read a file and then attach it to an email, what's going to get attached is the full original thing. Now on disk it's still in its compressed format, but as you read it and attach it, it's going to get expanded. There are some workflows, and Google will probably talk about these, where there's an advantage to keeping things shrunk as they move through a workflow. So backup is one of those. There's no reason to expand things when you're going to back them up. You might as well keep them shrunk. Replication is another one. There's examples, let's say that you want to run a big compute job on a cloud. Well, move the data set in a shrunken format into the cloud and then expand it there, because we have some pharmaceuticals who do this with Amazon. Amazon has bandwidth charges and megabyte charges. So if you move the data to the EC2 in its compressed form, you'll pay a lot less of their bandwidth charge, and then expand it as you run the compute job. So we do give you a way to access files in their shrunken form and keep them shrunken for workflows where that makes sense. But by default, if you access them through the reader will always expand them for you.
What about latency? If you're going to pack it through that much math, you're going to incur a penalty.
Yeah, that's a very good question.
I haven't seen you address that anywhere in your...
Yeah, and and the reason is because it depends so much. So let's say we did dedupe only but no compression. Well then, in that case, the latency is very, very low because there's no decompression that has to happen. We just have to read the blocks and reassemble them. So performance in the dedupe only case can be very close to what it was without us, right?
Yeah.
Then the next step up would be, let's say it was a simple file format like text, and we used a fast simple compressor. And we have our own, but let's say LZ is a good example of that. It's very fast. You can run at wire speed, and so sure there is decompression that's happening, but you won't notice it. There's maybe a 2 millisecond startup latency, and then the stream of data will happen at wire speed. You won't notice that it's being decompressed. Then let's say the worst case, H.264 high definition video, or one of these giant 14 megabyte photos. Now we've used a very complex compressor, and so the decompression is also complex, uses a lot of CPU cycles, and there will be more latency on the startup as the context gets built up, and the stream rate back will be slower. And because we have 100 different compressors and you can dedupe on or off, there's no one answer that says, well, how much slower does Ocarina make it? Right? It can range from hardly any slower. In fact, we just did a thing with a seismic customer reading terabyte-sized seismic files down in Texas, and he said running his geoframe and Petra applications that his scientists couldn't tell the difference at all reading these terabyte files. But that's because their seismic compressor is pretty fast.
Well, it's not real time either.
Yeah, that's
Reading
true.
seismic data is not a real time activity. All you've got to do is get it in and out of the I/O channels.
That's
so you can
right.
analyze it, right?
And
it's not
you
like
know,
watching a movie where you've got to decompress and recompress. If you're actually trying to stream that in real time, then the latency becomes obvious or clear.
it does at some point. So let's say that I add 10 milliseconds of latency. You're not going to notice that. That's
No.
not human noticeable. But if I add, 5,000 milliseconds of latency, absolutely you'll notice
Well,
it.
two things
Right?
there.
So-
Not only is there latency, but there's also jitter.
Yeah,
So if you have a video,
video.
compressor that all of a sudden starts
That's
to
right.
accelerate as it moves through a certain part, and then
that's right.
deaccelerates in another part, how do you address that? Because you're going to have to then run buffering algorithms.
That's right.
To
So
manage
one of the things is if we add a compressor, we say we support this file type. That means that we support it in the way that it's intended to be used. And you'll see that video, for example, is something that we've only introduced right now support for a very limited number of video codecs, and those are the ones that we can stream back without jitter and without you saying, hey, what the hell's wrong with this video?
Yeah.
Because that is a hard problem. Video is one of the most complex things to compress. It's already been compressed by smart people. Compression and video go hand in hand and have for years and years. So when we say we compress video, what we're really doing is recompressing, taking something that was already compressed pretty well and now trying to compress it even more.
I guess my
It's
concern
hard.
stems around is that you're putting your algorithms in software. Now, in the last 20 years, everybody who's done compression does it in silicon because it doesn't work in software or doesn't work well. So how do you, if I'd loaded that criticism at you, how would you address it? Would you say your software's smarter, quicker, faster, better?
Yeah, a little bit.
Or
There's
it's got
really two
more
parts to it.
horsepower?
One is that we do think that we have faster, more efficient algorithms, and our patent portfolio of how many patents we've gotten on compression is a bit of a testament to that. So we do think we've moved the needle forward in that. But the other thing is that having nothing to do with Ocarina, processing cycles have gotten cheaper and more plentiful. So today, in our appliance, our default processor that we use in there is a 6-core Dunnington.
Yeah.
Well, so a single processor, it has 6 cores. The amount of compute power in that standard commodity chip from Intel is more than you would have gotten in a mainframe 10 years ago. It's just, more cycles for lower price. And so at the highest level, one of the things that Ocarina is saying is that trading off CPU for storage right now is a good economic trade-off because of the nature of that. Even though disk prices are going lower and lower, if I can say buy 4 Intel processors and save you a petabyte of disk space, even though disks are cheaper, that's still a good, I can go buy an Intel server with, 2 6-core processors for, I don't know, what, $4,000 or something, $5,000?
Aside from 2-to-1 compression, like tape devices, what silicon has ever been better than software compression?
Heaps.
Huh?
Heaps.
For performance, I don't think the shrinkage result isn't better in silicon, but what has been better historically is that silicon can do it faster.
Well, that's why you have companies like Data Domain who are using commodity components to do inline dedupe at a very
Exactly.
high rate.
That's right.
People doing it in software just haven't got to a mature stage in their industry to cut a piece of silicon.
Right.
What it shows is that companies in early stage development of cycles use software because it can iterate fast until your portfolio stabilizes, and then they'll cut a piece of silicon to get the acceleration that customers need to scale. Right? Now that's the historical story.
That is absolutely right.
And the data domain just hasn't finished their development cycle.
Yeah,
They're still at early
That's,
stage.
that's only if you need it. I mean, if you look at companies like EMC, their arrays are not built out of ASICs doing storage.
Yeah.
It's using commodity components, and Data General's been doing that for the last 10 years.
Because storage isn't finished yet. It's still early stage product cycles. They
Yeah,
can't put it into
this sort of
silicon.
hardware versus software
still
argument
using
is it's a pendulum. There's no right and
Yeah.
wrong. It's a thing that
Yeah.
goes back and forth all the time. One of the things for us, though, why we prefer to stick with software and standard processors is because we have so many compressors. and we're adding new ones all the time. So if we had one compressor that we thought was the greatest thing since sliced bread, it probably would make sense to go implement that in silicon.
Yeah.
But we have 100 and something compressors, and we don't know in advance when we go to a customer what mix of files they're going to have. So the software figures that out. If you have that many different compressors plus the dedupe, it's too much stuff to put in silicon. It's better for us to leverage just the commodity, you know,
Well, certainly cheaper.
processor prices. That's right.
It's cheap.
So I'm not going to talk about this, but afterwards, feel free to ask me how we've done the integration with specific storage vendors. There's some pretty cool ways that we've made our stuff transparent to storage. Yeah.
Yeah, got a question for you. Obviously, with the uptake and virtualization, like more companies running VMs and what have you, what sort of CPU and resource utilization do you see on your software-based compression? Is it really dependent on what it's trying to process at the time? And
Yeah.
have you done any tests running it as a VM, like whether under sort of
Oh,
ESX
us
or
as a
Hyper-V?
VM. That wasn't the question I was expecting. Because we get great results shrinking virtual machines, and that's very fast because it's dedupe-centric, not compression-centric. We do run as a virtual machine. We don't do it in production yet, but we do it as a way for customers to measure how well they'll do if they bought our software. So we'll give you a little VM implementation of our stuff. You can run it against a test data set. And you know, if the results are 5%, you're going to say, oh, well, that's not interesting. If they're 80%, you're going to say, you know, bring me in the real solution and I'll test it in my lab. So as VMs support more threads, because the big thing for us is having access to lots of cores. So, you know, as virtual machines do a better job of giving you access to all the cores in a machine, it makes lots of sense for us to do implement our stuff as a virtual machine. And then you can run it on any platform that supports.
So potentially it
VMware.
is, I
Yeah.
suppose, depending on what you're trying to achieve, what
That's
you're trying to
right.
compress. So otherwise it'll just saturate all the resource
That's
on
right.
your host.
That's right.
Is that right? That's great, thank you.
Is Ocarina certified by VMware?
I don't think we are. We are certified with by EMC, so that includes a bunch of tests. Their certification process of VMware files, VMDKs, but we haven't done anything directly with VMware itself. We get smoking results on the files, though. They're because of the nature of virtual machines, they're just really good candidates for dedupe.
All right, thanks, Carter. Appreciate